Video. Okay, this is the first video in the sort of crash course in geometric transformations. So for the folks that are going to be teaching in Jamaica, although anyone else who wants to use this can certainly use this. So this is, I'm going to quickly go over Roman numerals 1, 2, and 3 on the outline of content that I gave you here. Again, just as a crash course. I think that the content is pretty intuitive, so we'll just kind of fly through this. It shouldn't be too difficult. I'm not going to go through every single item on the outline, but I think I'll go through enough of it to give you a feel for what these particular transformations are all about. So starting with the translation. It's a pretty easy one to do, and I'm just going to start with an example to illustrate it. So if we have a triangle ABC with vertices, 1, -3 for A, B is 2, -4, C 2, -1, just as I have drawn over here. If we translate triangle ABC according to the vector -4, 3, what are the coordinates of the vertices of the image triangle A prime, B prime, C prime? So really this translation vector, it's just a roadmap for you. Very easy. The first number is the x direction that you need to move your shape, and then the second number is the y direction that you need to move your shape. So if we translate triangle ABC according to this translation vector, okay, clearly then this becomes our image. Okay, for example, notice that to produce this image, I moved the point A, -4 in the x direction, so 4 to the left, and then I moved it +3 in the y direction. So A prime, the image, would end up being right here. Similarly, you could do the exact same thing for the other vertices. So B, if I go 1, 2, 3, 4 to the left, and 1, 2, 3 up, there's my B prime, and likewise I can produce my C that way. Of course, the answer that they're looking for here, if I was a student, I would say, okay, well, the coordinates of the vertices are A prime is at what, -3, 0, B prime is at -2, -1, and C prime is at -2, 2. Okay, so that's translations in a nutshell. Here's a variant on that. Let's say that I give you the object, the original triangle, and the object is the word we use for the original triangle, and I also give you the image of that triangle. Okay, so the way I phrased the question here, triangle ABC is transformed in the plane to produce its image, triangle A prime, B prime, C prime. Completely describe the transformation that has occurred. Well, hopefully you can see that this has been a translation, right? The original triangle simply moved. It didn't flip, it didn't turn, it didn't change sizes, it just moved somewhere else. And specifically, I can see that the triangle basically moved 3 to the right and 1 down. For instance, if you look at the movement from B to B prime, obviously that's 3 to the right and 1 down. Likewise, A to A prime will be 1, 2, 3 to the right and 1 down. C to C prime is 3 to the right and 1 down. So the answer to the sort of the task that was posed is that triangle ABC was translated according to the vector 3, -1. Okay, so translation should be quite easy, and I'm sure, another option is, you might be given a problem where you're given the image and you're given the translation vector, but you're not given the original object, and obviously then you would just sort of kind of reverse the translation vector, right? Because you need to go backwards to get from the image back to the object. So translations are pretty easy, I think. I'll talk about reflections for a little bit. So and starting just with a qualitative feel of what a reflection is. A reflection happens when something is reflected, when it's sort of flipped over a line. Whenever you reflect an object, you need to have a mirror line. In this case, I see that sort of this object, triangle ABC, which is located here, has been flipped over the x-axis. In this case, the x-axis is the mirror line that produced this reflection. And just to kind of show how the mirror line behaves, you're always going to have sort of this equal distances thing whenever you're reflecting across a mirror. So for example, the point A is 2 units away from the mirror line, which is the x-axis, and therefore the image of A prime, should be 2 units away on the other side of the mirror. Okay, it's truly just like a mirror like we use in our homes, right? If you stand 5 feet away from your mirror at home, your reflection is going to appear to be 5 feet away on the other side of the mirror. Okay, C is 2 units away, and hence C prime also has to be 2 units away from the mirror on the other side. And B was 3 units away from the x-axis mirror, and so B prime is 3 units away on the other side of the mirror. The mirror doesn't necessarily have to be vertical or horizontal. We can have a diagonal mirror line. I would say for the Jamaican kids, if they do have a diagonal line, it's always going to be a line that has a slope of either 1 or -1. You'll never get a slope of like 2 or 3/4 or anything like that. You can count on your mirror line always having a slope of 1 or -1. So just to illustrate that whole distances property, if I reflect the image A, B, C over this diagonal mirror line, notice that my distance property still holds because we define distance from a point to a line as being a perpendicular distance. So if I start at B and I move perpendicularly toward the mirror line, this distance here is sort of 2 diagonals is what I'm calling it. I mean, if you want to pull out your Pythagorean theorem, I guess technically this distance is 2√2. But it's easier for me just to count it as diagonal. So if I count diagonally perpendicular to the mirror, 1, 2, that's the distance of B to the mirror. Hence B prime needs to be 1, 2 on the other side. Okay? C is a distance of 1, 2, 3.5 diagonals from the mirror, and hence C prime needs to be a half, 1, 2, 3, 3.5 on the other side. A would have been a distance of 1, 2 diagonals, and hence A prime would be 1, 2 diagonals on the other side. Now you can imagine if you're doing this with graph paper with kids, the kids can actually fold the paper, right? And you get a real nice, the crease ends up becoming the mirror line, and you can see how one shape clearly maps onto the other one. So in some ways, graph paper is even superior way to illustrate this than this computer imagery that I'm using right now. Okay, reflect. Oh, this should be Roman numeral 2, so let me change that. 2B, given an object in a mirror line, find its image. So for example, if I have triangle ABC with vertices as follows, there it is. I want to reflect it across the line y equals x. What are the coordinates of the vertices of the image triangle A prime, B prime, C prime? So, I'd probably start by actually drawing that line y equals x, which is a diagonal. It's the red line here. Okay, that's the mirror line, y equals x. Since it's diagonal, I know I need to count diagonally. So, for instance, if I start with the point A, how far is A from the mirror? Well, it's 1, 2 diagonals away from the mirror, and hence A prime would have to be 1, 2 away on the other side. C is 1.5, 1.5 for C prime. B is a distance of 1, 2, 3 from the mirror, 1, 2, 3 diagonals. So there we go. I've drawn my A prime, B prime, C prime, and right over here are its vertices. Okay. Here's another task students might do. Given an object and its image, find the mirror line. So for example, here the problem is telling me that here's my object, here's my image, and the question is, well, what happened here? How do you map triangle ABC onto A prime, B prime, C prime with a single transformation? Hopefully the student can just see, well, it appears that the object just flipped over. So, but we need more than just saying, well, it flipped. I mean, you need to be specific and say what the mirror line was. Okay, so we're just looking for kind of a line that's clearly halfway in between the object and the image, which would have to be this line, right? Notice again, A is a distance of 1, 2, 3 from there. A prime is 1, 2, 3 on the other side. C is 1, 2, 3, 4. C prime is 1, 2, 3, 4. So this is the mirror line that splits it perfectly. That's exactly halfway between the object and image. So we would describe this transformation as a reflection with a mirror line of x equals -2, since the equation x equals -2 happens to describe that line that is serving as the mirror. Okay, the last thing in my crash course for this part, for video 1, glide reflection. And a glide reflection is simply a combination of a translation and a rotation. One thing to note is it's not just a straight up any old translation followed up by any old reflection. The translation vector will always run parallel to the mirror line. That's kind of an important aspect of the glide reflection to kind of bear in mind. So for example, here's my triangle again. We've seen it before, ABC. If I undergo a glide reflection involving a translation of 4, 0 and a reflection across the x-axis, let's find the image. Well, I'm going to cut right to the chase. It's easy to translate the triangle 4, according to this vector, because this is saying move 4 in the x direction and 0 in the y direction. So if I take point C and I go 1, 2, 3, 4 in the x direction, I'd end up right here. A, 4 in the x direction, B, 4 in the x direction. It gets me here. This is the preliminary stage. That's the first part of the glide reflection. Then I need to reflect this thing across the x-axis to get my final image. And again, that's pretty easy to do, to reflect it across the x-axis. C is 1 away, so C prime is 1 away on the other side. Okay, A is 1, 2, 3 away, A prime is 1, 2, 3 away. So that's kind of where this thing ends up. Notice how the translation vector was kind of straight to the right. Okay, and I'll even draw a picture of that. It's kind of like the translation did this. Oh, golly. And notice also, okay, it moved 4 just straight to the right. Notice also that this vector is parallel to the mirror line, which was the x-axis. So if you did a glide reflection that was diagonal, you would expect the translation vector to be diagonal. You might have a translation vector that might be, say, 4, 4, right? Move 4 to the right and 4 up. And that would be perfectly parallel to a line having a slope of 1, that sort of thing. So, okay, so again, that's the crash course. Tune in to the future episodes of this video for information about the other transformations.